Hello everyone, it's me, Matt Thomas. Today I'm going to start my video series for my internship. This is an ongoing project I've been doing for about a year and a half, 2 years now. And it's for the microbiology department as well as the mechanical and aerospace engineering department. So, a little bit about me and this project. As you notice, it was called Is It Food Safe? That is the tip of the iceberg. That is the end of the project and what we're trying to accomplish. But there's so much preliminary stuff that's happened before, and I'm going to be discussing all that preliminary stuff. It's part of my internship. This is the data. This is where we've started, and this is where we're going to end. Where we're going to end with. Now, the internship is not over, so we're about 3/4 of the way done. Doing all the stuff. Now we're in the hardcore stuff of actually proving a hypothesis. So a little bit about me. I am an aerospace and mechanical engineer. I have experience in the field of materials, advanced materials, and medical devices. I have a minor in drafting, math, materials, and courses in medicine such as anatomy, pathophysiology, chemistry, organic chemistry. I am a certified phlebotomist. I can draw people's blood. Don't really do that much, but I can do it. And microbiology. So before I became an engineer, my background's very, very varied. I have a bachelor's in cybersecurity and network engineering, so I worked for the Department of Defense when I was about in my early 20s in a cybersecurity team. That was fun, got burned out, I enjoyed it, but it was more of a hobby, so I want to stick with that as a hobby. I grew up with a mother who was a head nurse of a research facility up here in Utah, a research hospital, for 22 years. She's extremely smart. Even though she's moved on and passed away, she is still the smartest woman I've ever met in my life. She was on the team that helped install the first heart transplant back in I want to say it was the late 70s. And so just all these inspirational stories growing up. So I wanted to go, my mom is my hero, so I wanted to follow in her footsteps. So I started taking microbiology, biology, chemistry, organic chemistry, all these medical classes. It was great. I learned a lot. But the biggest thing I learned was she's better at fixing people than I am. And I'm better at fixing machines than she is. So I switched to mechanical and aerospace. And having that background in medicine and chemistry has helped so much with my aerospace engineering. It's just unbelievable how they actually correlate and mix. I mean, the human body is the ultimate machine, if you want to think of it that way. And everything that happens in it, even in my fluid dynamics course, I related so much of the pressure gradients and the streamline functions to how the human heart works with the pump and the valves and everything. There's just so much. And then machine design, if you want to, you look at, you have shafts and pulleys and stuff. Well, you've got bones in your body, the femur, and then stresses and how things work with that, torsion fractures. I mean, it's kind of it's all similar. So it's really awesome. If you guys want to know more about me and some of the things I've done, you can check out my portfolio. There's the link right there. Also, the mask relief project that I spearheaded as an engineer during COVID. You can check out the resources there. I have videos of me 3D modeling a N95 style respirator, and we talk about filters and everything like that. And that's actually part of this internship. It's all related. So you can go through that and watch the videos. I show step by step actually how to model something. And I have posts on there and just so much information. So continuing forward, how did this project start and my reasons behind it? It actually all started right around COVID. I'm talking, October 2019 is when we started hearing about this COVID situation going on and the possibilities of this pandemic. And then all of a sudden it hit in March with shutdowns. And so what ended up happening was so many people were staying at home, and they were printing cookie cutters, toys for kids, they were printing masks and face shields, they were printing all sorts of stuff, and a huge concern came up of, well, okay, are cookie cutters food safe? I mean, I'm staying at home with my kids, and is this cookie cutter food safe? Or what about this spoon I printed, out of plastic, PLA or ABS or whatever for, eating soup with? Is it food safe? And then people are saying, well, all these masks and face shields we just made and 3D printed, can they be cleaned? I mean, those are legitimate questions. I mean, in the everyday life, when we do dishes, we don't really think about, oh man, is this clean? Am I going to get sick from this? We don't really think about that because we kind of blindly trust the manufacturing process. And then all of a sudden, we make something of our own. We can make our own cutting board out of walnut, and then we'd question the integrity of it, because that's what human beings do. They question their own integrity and their own selves. And so now we're just questioning, okay, can these 3D printed things actually be cleaned? And that was a huge question. And so that's when this project started, because I started doing all the math and the research, and I knew they could be cleaned, and I started trying to show the math of how to do it and talking about it. And so the answer to can they be cleaned, as in getting rid of bacteria and so forth, the answer is yes. But that doesn't necessarily mean it's food safe. But at least for masks and face shields, at this starting point, yes, they can be cleaned and sanitized and you're fine. Now, the other reason was fake science. I don't know why or what happened in the world in 2020, but in 2019, people understood science and how things worked. They understood how viruses worked. You could read it in a 5th grade biology book. And people were like, oh yeah, that's cool. Then 2020 hit, and everyone is now posting on the University of YouTube, and now they're all self-proclaimed doctors of science. They work for OSHA, and they work for the CDC or the WHO, and they're saying all these things, and then you find out they don't work for OSHA or the CDC or the WHO. They don't work for anyone. There's some political agenda or some random person at home trying to spew their own opinion, and they know just enough fake science to be dangerous. And so they just know just enough that it makes it dangerous for people because it's incomplete. And it sounds good, it sounds pleasing, and then what happens to people is it feeds people, and then people are like, oh yeah, that makes sense, and then they make their own conclusions based off of fake, incomplete, inaccurate, utter, for lack of a better word, BS. There's no other word to describe it but BS. And so my goal has been to try to educate people so that they can make their own choice and do what they want. And so this whole internship is just to show how science works, why it does what it does, how cleaning and sanitizing something works, and to give it to the community, because in the 3D printing community there's so many questions about cleaning and sanitizing. So I'm going to try to do this the best I can without being too boring. There's a ton of information, so if you need to put this on 2x for the speed, go for it. Just remember, there's a lot of information and I don't want you guys to miss anything. Okay, so this is how things work. Let's just start with bare bones basics. Let's talk about some viruses and bacteria here. According to the Encyclopedia of Medicine, and Britannica, and Wikipedia, and any microbiology book, a virus is a submicroscopic infectious agent of simple composition that replicates only, huge keyword right there, only, inside much larger living organisms. It's that simple. That's it. A virus is non-living and cannot reproduce. It has to replicate. The only way it can replicate is if it burrows itself into a much larger cell, uses that cell's organs, lipids, food resources, and energy resources to replicate more viruses. Then those viruses, when the cell gets too big, it explodes, and then those viruses go and infect other cells. That is it. That is it on. I mean, that's it. You could go find a 5th grade biology book at the public library or the internet or wherever you want your source to be, and it'll say the exact same thing. Now, bacteria are living organisms and they can reproduce. They are different than viruses. Now, when a virus takes over bacteria, it's called a bacteriophage. Happens all the time. But viruses need a living host cell. Fun fact, the smallest host cell in micron size that can successfully allow replication of a virus is 0.4 microns in size. Anything smaller than that, the virus cannot successfully replicate. It's just not enough resources for it. So, that information's been known since about 1973. And we've known about viruses for at least 200 years. It was first studied with rabies underneath a microscope. And so, that they need a host cell in order to replicate. They're kind of like, if you really think about it, a baby is kind of like a virus. It needs a host cell in order to live. But then when it leaves the body, it can live on its own. Actually, it's more like a parasite then. We'll go with that. Weird analogy, I know, but if you think about it in biology terms, there you go. Okay, the next thing you need to understand is something called surface tension. This is the property of a surface of a liquid that allows it to resist an external force. So when you have a drop of liquid on something, the more it can hold its shape in a spherical pattern means it has more surface tension. And it's resisting external forces around it. Whatever those forces are. That's including gravity, that's including pressure, that's including a bunch of other forces, and it can hold its shape. So here's the thing. There's something called the contact angle and the wetting angle, and with water, it has a very high surface tension, about 73 dynes per centimeter. That's a dyne is a type of force over force over area, so dynes per centimeter. So it's 73 dynes per centimeter for water. It's pretty high surface tension. So you can do a wetting test, which is when you drop a drop of water on something, and when it beads up, the more spherical it is, the less area that it's actually getting into that surface. So if you have filter material, you put a drop of water on it, the higher the contact angle or higher surface tension, the larger the pores have to be in order for that water to get into it because of that surface tension. So, what makes soap so amazing is it lowers that surface tension of water drastically by about 50 points. I don't want to say points, by 50 dynes. So you add soap to water, it goes down to 24 dynes per centimeter. And it can actually get into pores as small as viruses. And soap is amazing. Soap is freaking cool. My wife and I make homemade soap. Well, I mean, we buy soap from the store, but it's fun to make your own. It's just kind of a fun experiment. But what soap actually does is when it finds bacteria or other cells, it doesn't matter what kind of cell, good bacteria, bad bacteria, as long as there's fat in it, it will turn that fat and saponify it into more soap. So you're literally turning bacteria into soap. And that's what's really cool about soap. It's just fascinating to me. So, soapy water can actually get into pores as small as viruses. Now, rubbing alcohol is 23 dynes per centimeter and can actually get into pores smaller than viruses. And it's actually required in labs and medical facilities to use 70% or higher isopropyl alcohol because of how small pores it can get into. Soapy water can get into pores just as well, but the reason why they're required is because it's just, it can get into pores smaller than viruses, so they like having that extra space, especially in medical facilities where they're dealing with stuff more than what the general public and homes deal with. So that's kind of some basics. Now here on the left you can see some of the fabrics, actually one fabric. This fabric right here is what we took underneath the scanning electron microscope. This is 600 threads per inch cotton. This is what it looks like underneath a microscope. It's actually kind of cool. And then right here is the mask that I designed. It has a complete open face right here to allow for a lot of breathing. And we did a lot of filter tests and a lot of other testing with materials and masks and sanitation. Like I said, we just didn't just come up with random things and say, oh, blah, 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 blah. No, I did tests. We did tests. This is not just a fly-by-night thing. So, moving on. This is in more of how things work. To the left is the math that I use from fluid mechanics and particle physics. There's something called the psi function, and there's also something called Brownian motion. There's particle diffusion and flux. And if you've ever had fluid mechanics, there'll be something you'll learn called the Navier-Stokes equations, which are really cool. They're easy to simplify, but there's just tons of them. And it's about two-dimensional flow, but if you get into three-dimensional flow, don't do these by hand. You're going to have to use some sort of computational program such as MATLAB. I don't know if Maple will do it. I doubt Excel can handle it, but I know MATLAB. And there's other programs. MATLAB's not the only one. So use what you know how to use. Octave is open source, and it can do this. Okay, so the psi function is the difference between a stream function values at any 2 points. So you have a line, you have point A and point B. The psi function is the difference between the two stream function values at those points for the volumetric flow rate, or the volumetric flux, through a line connecting those 2 points. This is important because think of a car driving down a highway. You've got streamline functions going over it because of its aerodynamic and the air. So as air moves over the windshield, you have these streamline functions. Now, certain bugs will follow that streamline because their density, their pressure gradients, and everything that's going on with that bug is pretty similar to air. And then the ones that hit your windshield are the ones that don't match that streamline. They're called a path line, and they follow the streamline but sometimes go out of the bounds a little bit, and then they hit your windshield. That's because they're following the path line. So think of a piece of pepper or a piece of driftwood on a river. The river's a streamline, the driftwood is a path line, and as it flows, it can, it can follow the river, but it could hit the bank, it could hit, other things in the way. So air is very fluid, it's the same thing. Then we have what we call Brownian motion, which is the study of particle motion suspended in a medium such as a liquid or a gas, which relates the streamline function psi and Brownian motion based on the diffusion principle. So basically what Brownian motion is how particles react and behave in a fluid. And since air is a fluid, we're looking at how do different sized particles react in the fluid. Turns out that large particles, and I'll get into this later. You know what? Actually, no, let's do it. Size does matter. Perfect. So, large particles actually are heavy and massive and pretty much fall to the ground. Small particles bounce off of other molecules in the air, such as nitrogen or the air molecules or other gases in the atmosphere. So when a material states that it can effectively filter out 95% of 0.3 microns, this does not mean that 0.3 is the smallest. In fact, N95 material can actually capture more particles that are smaller and larger than 0.3. And the reason why is because 0.3 is the hardest the hardest particle size to capture, because we have found that at 0.3 microns, it follows the streamline. It follows the path, so it's very linear. It follows the same pressure gradient and the function as air, and it's just very linear. So it's like literally throwing a softball through a soccer net. So we have to come up with ways to counteract that. And N95 material, even in your furnace filter, when you go to Walmart or Home Depot or a box store and you look, hey, I need to pick up a 3M filter for my furnace, and you look at it, and it's the 1500 advanced allergen, and it says this is what it can all block out. If you look at the back, it'll show a picture of a magnet. And what that magnet means, it'll say electrostatically charged spun polypropylene. And N95 material is made from this exact same material, electrostatically charged spun polypropylene. And what that is they put an electric charge on it, so when particles that are extremely difficult to capture float linearly through it, the material is statically charged that it will act as a magnet and suck the particle to the material. So think of throwing a softball straight through a net, but now it's a metal softball and the net is a magnet. It'll just suck it right to the net. So that is how that N95 material works. It's also the same thing that's in your furnace filter, as long as you get the stuff made by 3M. Some of it has fiberglass, some of it doesn't. HEPA filters I do not think are statically charged, but they're harder to breathe through because of how tightly woven they are. That's why I prefer melt-blown, electrostatically charged spun polypropylene. It's just easy to breathe through and it makes sense. And in fact, they make large sheets of it and then they cut it off, send one group for masks and one group for furnace filters. I know some of the 3M engineers, and manufacturing is all about being efficient, right? So, one of the things people ask is, well, if you can smell things through the material, then that means it's not blocking. Well, you got to remember particle size. So a virus that's 0.125 microns in size, okay, is going to be extremely easy to capture because it bounces off air molecules. But remember, sulfur, we can smell sulfur through a mask, and it's 300 times smaller, 320 times smaller than a virus. You can smell methane through a mask, and it's almost 400 times smaller than a virus. So you just got to remember about particle size. Now, I did say viruses are 0.125 microns in size. That is absolutely true. But remember, viruses absolutely must need a host cell in order to replicate. We do not breathe out a naked virus. We can't. It's impossible. If I'm sick with the flu or a cold or some other virus and I'm breathing like I am now, talking and just breathing, I'm breathing out infected host cells, not a virus. That's very important to remember and to know. We do not breathe out a virus. We breathe out infected host cells. And remember, the largest host cell that can successfully allow replication is 0.4 microns. Just keep that in mind. Okay, let's look at these filter tests. This is going to be the last section for this particular video. Again, on the left-hand side, we have mathematical equations. If you know these equations, that's awesome. If you don't, that's awesome. Don't worry about it. The top one is the psi functions and volumetric flow rates. Bottom one is Brownian motion and diffusion. So I'm just showing you that I use real math. I don't just make up stuff. I use real math in order to get data. You have to. Math is the language of science. There's no ifs, ands, or buts. Okay, so when it came to tests, what we did is our group, we have a volume chamber that you put material around, and it tests the flux of material to see how well particles can move back and forth, the diffusion of it, the flux. So this can be good for at least just testing filtration, but it can also lead to inaccurate results of, well, what about gaps in the mask? And I'm going to address that here next. So let's talk about these volume chambers first. So when we put melt-blown polypropylene, you can see here on the table that it was 96% 95% efficient for 0.1 micron sized particles. 96% efficient against particles the size of a virus, if we did breathe out a virus, but remember, we don't. However, if we did, it wouldn't matter because 96% is filtered. Now, above 0.3 microns, it's 99% efficient. Melt-blown polypropylene. Okay, that was our control, and that was with a 5% gap around the PVC pipe to allow particles to flow behind it to simulate gaps in masks. That was our control. A cotton quilt, 96%. Cotton single layer 600 threads per inch, 82 and 98. And then a hybrid of one layer of the cotton, of the 600 TPI cotton with a layer of silk. You can see that. Now when I say cotton quilt, I mean I'm talking about a piece of quilter's cotton in the front, followed by half a centimeter of batting material, followed by another cotton piece, like an actual quilt, like a small little cheap quilt that you cut and made a mask out of. So it'd be hard to breathe, it'd be a little warm, but it would be great for winter and snowboarding. But I mean, you don't need a mask out in open air, there's no need. But it would keep you warm, at least for snowboarding or skiing or winter activities. I mean, I wear some sort of face covering for staying warm, but for a mask, cotton quilt, I mean, it would work. It does very well, but it's uncomfortable. But what I thought was interesting was the cotton silk, the hybrid with that. And you can electrostatically charge the silk. It can actually naturally charge itself. And fun fact, do not get melt-blown polypropylene wet. Do not wash a mask because water kills static. So with silk, if you wash it, you're going to have to recharge it. I mean, you can do that with a plastic rod or rub it together, you know. So, but even without an electric charge, it still did very well. Even, this was with no charge. This was right after washing the mask we tested it, the materials, and it was 94.98. Okay, so this is very good for at least testing the filtration, and we tested it with 100% fit and with a 5% fit, a 5% gap. And then we wanted to say, okay, that works, but the gaps around the human face, the contours of the cheeks, the skin is sticky, things are going to stick to it, facial hair, particles will stick to your face. We need a second way to test filtration, and we want to do this with live subjects. So we used what we call, in biology, the gold standard for testing pathogens and growing things is Petri dishes. Petri dishes have been used for years and years and years because that's how you grow bacteria and viruses. That's just the best way to do it. There's no other way to culture except on a Petri dish. Petri dish will not lie. You open it up, if something falls on it, it will grow like wildfire. It is a pandemic in a container of anything. You leave it open to open air for 5 minutes, close it, you will grow stuff. So this is where I came in. We make our own Petri dishes at lab by the hundreds a day. So we used, for this internship so far, we're using, just to test the 3D printed stuff, I've used 100 Petri dishes. To test filtration stuff, we've used another probably 50 or so. We've used a couple hundred Petri dishes. We're close to it. So what we did was we just used live infected people. I was sick with COVID. I also had the flu. I also had mono. We're always getting sick with something. And so when I was sick, I was just like, this is a perfect time to test. So, I get different types of materials. I got melt-blown polypropylene. I got cheesecloth, a paper towel. I got my cotton mask. I got my 3D printed mask. I got an N95 mask. I got a basic surgical mask. We did all these tests, and with multiple people. I wasn't the only one either. There was other people who were sick with things. My wife was sick with things. She came to the lab. Other friends and colleagues were sick. So we just had fun and just did tests. Why not? Why not do tests when you're sick? it's the best way to collect data. And so we did that, and we found that not a whole lot grew. And I have pictures of it, and I have a whole other presentation on that, which I can show later. That, we without masks on, a whole bunch of stuff grew. With different materials on, different rates of of pathogens that had the virus in it. A virus in it, not the virus, a virus in it, growing. And you also have to remember that not every breath we breathe out is going to be infected. I mean, they can only replicate so fast, and then your immune system kicks in, so, the viral load that we breathe out is limited. So, I mean, there's more particles in one puff of cigarette smoke. There's about 1 million times more particles in one puff of cigarette smoke than we'll ever breathe out of a virus in 20 minutes. So, I mean, you have to keep those kind of things in consideration. And so this was all a whole lot of fun to do. We did a lot of preliminary testing with this and just started growing things and writing down the data of how much viruses actually grew. And with a standard cotton mask, like loose fitting mask, we got one small colony. And that was from 1 foot away. The petri dishes that were 6 feet away, they didn't grow anything. Petri dishes even 3 feet away didn't grow anything. But when I say, what I did was, you hold the plate up, and we held plates up around even the gaps, and I yelled, coughed, sneezed, and screamed and sang. And we did that to multiple people, where you have dishes around the gaps and even in front of the mask. One colony. One very small colony the size of a pinhead. And we let it culture for 4 days, and then we even let it culture for 2 weeks, just to see, and it stayed the same. So it was really interesting. And then we had our results validated by the American Chemical Society, because we worked with them, and I shouldn't say validated by them, we worked with them, and so they took our data, and it was their volume chamber and whatnot, and then they helped publish the data, and bada bing, bada boom, and so that's where these numbers come from. And so this is just how things work, and this is all gearing up towards, remember, this internship was threefold. This is all gearing up towards sanitizing. I know it's a lot of information, but it's the preliminaries. Alright, so at this time, this is where I'm going to stop, and when I start again, this is the slide we're going to start on. So thank you for listening. I know it's kind of dry. I know it's a lot of information. It's a ton of information. Fun fact, these petri dishes, especially here, I'm going to use my mouse, this one right here is done correctly. Whoever made this petri dish did a very good job. I can talk about that in the next video presentation. I just think it's really cool that this person did a phenomenal job at it. Anyways, thank you for watching, and thank you for staying tuned, and I hope you guys have learned something.